Hello students and welcome to the 48th lecture on particle physics. And in the last lecture, we have discussed Gibbs mechanism and saw that how charm quark was proposed by Glashow, Laplace and Miani. And today we are going to talk about the discovery of charm quark. Recall the Gibbs mechanism was placed in 1970 and today we are going to talk about November Revolution, and that took place in 1974. And what I had told you that independently at the two different laboratories, Brookhaven National Laboratory and Stanford Linear Accelerator Center, the experiments were performed. At Brookhaven, it was a laboratory experiment where there was a proton target and another proton was the projectile, and then the final states were observed. At SLAC, it was electron-positron collider, and their particles were observed in the final state. This is what we are going to discuss in today's class. Now, what I am telling you is that in 1972, Ting, a member of the Massachusetts Institute of Technology group, submitted a proposal to Brookhaven National Laboratory where the idea was to look for the vector mesons through fixed target production experiments in which high energy proton will strike a target like PP, and in the final state we have a vector mesons and then other particles in the final state. Here X represent anything and V represents a vector meson. In August 1974, during the analysis of the events, they found all the events piled up at 3100 MeV or say 3.1 GeV, a sharp and sudden rise of events resembling a needle. So therefore, this was something like this. This is the center of mass energy. These are the events. And we are talking about a sudden rise at 3.1 GeV. That means almost the event looked like a needle. That means a sharp increase in the event rates, or in other words, we can say that a big jump in the cross section, which was telling us that some resonant particle has got formed. The internal discussion and verification among the group members took a long time, and finally it was reported in November 1974. Ting called this particle as J. During the same time, experiments were being performed at the Stanford Linear Accelerator Center where they were using electron-positron collider. That means electron from this side, positron from this side, of equal energy and momenta, and they were colliding. And the existence of an unusually narrow hadron at 3.095 GeV, very similar to what was observed by Ting group, was reported. Richter called this particle as psi. The discovery of these two particles were reported to the Physical Review Letters, a journal published by the American Physical Society, and both the papers were published in the back-to-back pages of the same volume. Ting et al., the volume of PRL is 33 and page starts with 1404 to 1405, called the particle as J, while Richter et al. Called it psi. Again, this was published in volume 33, page 1406 to 1407. Looking at the properties of J and psi, it was found that they are electrically neutral mesons whose masses are more than 3 times that of the proton. Remember, proton mass is about 1 GeV. Therefore, we are talking about a mass which is about 3 GeV, approximately 3.1 GeV, and its lifetime was almost 1000 times larger than that of the other particles of comparable masses known at that point of time. And this was approximately 10 power minus 20 seconds. And remember, delta, which has a mass of 1232 MeV, it decays through strong interaction to a nucleon and a pion, and its lifetime is about 23 10 power minus 23 seconds. While we are talking about a particle which is more than 2.5 times the mass of a delta and whose lifetime is much larger than the lifetime of the delta, 1,000 times the lifetime is longer than the lifetime of a delta particle. These two particles were realized to be the one and the same particle, and hence the name J by psi, as the papers were published in the same volume of Physical Review Letters. The discovery was so important in the field of hadron physics, particularly to save the quark model, that the period is known as November Revolution. Remember what we were discussing on the last turn, that after 1964, Gell-Mann and Zweigman gave independently a eightfold way and argued that these nucleons and the other hadrons, they are made up of point-like objects, and those they call as up, down and strange quarks. After that, almost the things got stagnant, and then suddenly in 1970 and then in 1974, people started again talking about the quarks, and that is why this discovery of a new meson, J by psi meson, this period is known as November Revolution. Its impact on the development of high energy physics was so phenomenal that these two groups, led by Teng et al. And Richter et al., were awarded Nobel Prize for the year 1976. If you can see or have it some time to look at the papers of Nobel laureates, the duration during which they have worked and the period when they were awarded Nobel Prize, this takes almost 15, 20, 25 years for people to realize the importance of the work. But here in this case, within 2 years, 1974 in November the paper was published, and in 1976 the Nobel Prize was awarded. Similar to this, there is story of C.V. Raman also. For the Raman effect, it was proposed on the or declared to the press on the 29th February 1930, and he was awarded 1932 Nobel Prize. It happens rarely that within a few years of time, people realize the importance of the work and Nobel Prize is awarded. About 1 year of J by psi discovery, it was concluded that this J by psi is a bound state of charm anti-charm quarks, and hence the charm quark which was introduced through the Jim mechanism was confirmed by Richter and Teng group. Later, people observed charm baryons in 1975, followed by the discovery of other charm baryons like Cascade C, made up of up, strange and charm quark, and Omega C, made up of 2 strange and 1 charm quark. The first charm meson was discovered in 1976, and that was named as D0, which is made up of a charm quark and anti-U quark. And you see the charm quark has a charge of plus 2 by 3. Anti-U has a charge of minus 2 by 3. Therefore, this is a neutral particle. Then D plus, you see 2 by 3 is the charge, and D bar is plus 1 by 3. Therefore, the charge is plus 1. And you know these are the mesons. Therefore, the baryon number should be 0. And as you can see, for the charm quark, the baryon number is plus 1 by 3. And for anti-U, the baryon number is minus 1 by 3. And net baryon number is 0. Now, we have the 4 flavors: up, down, charm and strange. And in the weak sector, we wrote the doublets as, remember, U D prime and C S prime. And D prime was D cosine theta C plus S sine theta C. and S prime was minus d sine theta c plus s cosine theta c. Therefore, if we have U to D transition involving a W boson, then this vortex we saw is represented by GW cosine theta c. Similarly, if we have transition in the same second generation C to S, the vortex will be GW cosine theta c. But if we have the transition from C to D, then the vortex will be GW sine theta c. Therefore, remember, transition for the same generation has the vortex GW cosine theta c, whether it is U to D, D to U, U bar to D bar, D bar to U bar, or C to S, S to C, C bar to S bar, S bar to C bar. Always the vortex will be GW cosine theta c. And if you have the different generation, that means U and S, then the vortex will be GW sine theta c, or S to U, or U bar to S bar, or S bar to U bar, the vortex will be GW sine theta c. Or similarly, if you have C to D, or D to C, C bar to D bar, or D bar to C bar, the vortex will be GW sine theta c. That is why here I have written GUD, GUD, GCS, GCS involving up, down or vice versa, up U bar, D bar or vice versa, charm strange or vice versa, C bar, S bar or vice versa. And you see the vortex GUD is GCS is GW cosine theta c. And now instead of D, if we write S or S bar here, or here we write D, or here we write D bar, then the vortex will be GW sine theta c. Therefore, remember here GUD is equal to GCS is equal to GW cosine theta c. And if we have GUS, GU bar, S bar, GCD or GC bar, D bar or vice versa, the vortex is GW sine theta c. Therefore, this sine theta c is sine 13.1 degree determined through the experiments. That is an important point, that this was phenomenologically obtained and this value turned out to be 13.1 degree. Then after this charm quark, another story came. Till now we had nu e electron, nu mu muon, 4 leptons and 4 quarks. Everybody was happy with it. This is known by the name Glashow symmetry, as many leptons as that of quarks. But what happened? In 1975, people observed a new lepton that was much heavier in mass. Mass was around 1.7 GeV in the laboratory experiments. And if there is a lepton, then that means there should be a neutrino associated with it. And then Glashow symmetry is broken. But very soon it was found in the experiments that a new baryon and a new meson were observed, which could not be explained with the help of up, down, strange and charm quarks. There we required a much heavier quark, and that was the bottom quark. Therefore, in 1975, scientists at Stanford Linear Accelerator Center discovered the tau leptons, spoiling the Glashow symmetry. Now to each charged lepton there is an associated neutrino, and therefore nu tau was proposed. In 1976-75 we had 6 leptons and 4 quarks, setting off a search for 2 more quark flavors to save Glashow symmetry. Very soon at the Fermi Labs Tevatron accelerator, in the collision of proton with a fixed target at high energy, bumps were observed. Again, that means we are talking about a sudden rise in the cross section. This bump indicated the existence of a new meson which was called as epsilon meson, which could not be explained with up, down, strange and charm combination. And therefore, bottom quark and anti-bottom quarks were proposed. The first bottom baryon was observed to be lambda b with quark configuration of U, D and B in 1980s, and the other was sigma b plus that was made up of UUB in 2006. First bottom mesons were then observed with the quark combination of BD bar and BU bar. Therefore, like we have D plus, D0, D0 bar and D minus, similarly here we have B plus, B0, B0 bar and B minus. So therefore, this B minus is made up of BU bar quark, B0 bar is made up of BD bar quark. Similarly, if you talk about B plus and B0, then B plus, see here in the case of strangeness, the strangeness quantum number is -1. In the case of charm quark, the charmness quantum number is +1. In the case of bottom quark, the bottomness quantum number is -1. While for anti-bottom quark, the bottomness quantum number is +1. Therefore, mind it, it is B minus and it is made up of BU bar. Therefore, this bottomness quantum number is -1 and we have B minus. Similarly, if you think of B plus, then that should be B bar U. This charge is 2 by 3 and bottom's charge is -1 by 3. Therefore, anti-bottom charge will be +1 by 3 and net charge will be +1. Therefore, we have B plus, B0, B0 bar and B minus like we had D plus, D0, D0 bar and D minus. But here in the case of D plus, we write the quark configuration as CD bar and here we write it as C bar D. And mind it, the charmness quantum number CM for the charm quark, we are telling it is to be +1. Similarly, when we talk about the topness quantum number for the top quark, that is +1. Therefore, the strangeness quantum number is -1 for the strange quark. Bottomness quantum number is -1 for the bottom quark. And charmness quantum number is +1 for the charm quark. And the topness quantum number is +1 for the top quark. Therefore, if you have D plus whose mass is 1870 MeV, this is CD bar, D0 is CU bar, D minus is DC bar and D0 bar is UC bar. Similarly, a D meson containing a strange quark, this is CS bar. You know, charmness quantum number is +1. Since strangeness quantum number is -1, therefore anti-strange means it will be +1. This is SC bar. Strangeness quantum number is -1 and this is C bar. Therefore, charmness quantum number is also -1. Then we have B meson where the resonance corresponds to mass of 5279 MeV. The quark configuration is UB bar and you see this charge is U is 2 by 3 and B is -1 by 3 and B bar will be +1 by 3. Therefore, this charge is +1. This is how we have the different charm mesons, charm baryons containing a strange quark, containing non-strange quarks and all that. For example, lambda C plus is UDC. Sigma C plus plus, we have UUC. This is the UC, the charge is +2 because 2 by 3 plus 2 by 3 plus 2 by 3 would give us 2. Similarly, we have sigma C plus, sigma C0 bar, sigma C0, etc. And these are all the particles which have been observed in the laboratories. And then we have charm baryons with strange quarks also. As you can see, cascade C plus, where you have U quark and a strange quark and a charm quark, or omega C0, 2 strange quark and 1 charm quark. This is how we had this zoo of particles where hundreds of particles were observed in the different experiments starting from 19 50s, 60s and 70s and after that. And therefore we have then the bottom quarks and bottom baryons with strange quarks, as you can see, 2s and 1b. That means strangeness quantum number is -2. While if you remember, we had omega minus, whose mass was around 1680 MeV. This was made up of 3 strange quarks, but here we are talking about 2 strange quarks and 1 B quark. Therefore, this strangeness quantum number is -2. Here the strangeness quantum number is -3. But here we have bottomness quantum number, that is -1. Therefore, bottomness quantum number is -1. Topness quantum number is +1. Now recall, when I was discussing C parity, the charge conjugation operation, I had told you that we have parity, which is an operation of a spatial inversion, and then we have a C parity, where we takes particles to the anti-particle states, and here the quantum numbers like lepton number, baryon number, charge, sign of the magnetic moments, etc., they change, but the location of the particle, time, momentum of the particle, etc., spin, they do not change. And then we discussed that if we have a quark anti-quark configuration, since this is fermion and anti-fermion, the parity, if you can recall, that was given by parity of the fermion times the parity of anti-fermion minus 1 to the power L. L was the relative orbital angular momentum between fermion and anti-fermion. And recall that when we were discussing about electron, proton, lambda, muon, I told you that it is impossible to determine the parity of leptons, and therefore we put by hand or assign by hand the parity of leptons and parity of baryons, and traditionally we take the parity of electron, muon, tauon, or we call proton, neutron, lambda, sigma as particles. We assign them parity, intrinsic parity, to be +1, and then for anti-particles like positron, mu plus, tau plus, anti-proton, anti-neutron, anti-lambda, we assign parity, intrinsic parity of the particle to be -1. But the important point is that the Dirac theory of spin half particles, that is consistent when you take parity of fermion to be opposite to the parity of anti-fermion. Therefore, you can assign, we have discussed, parity of fermion to be -1, then you have to consider parity of anti-fermion to be +1. But mind it, the product of fermion times anti-fermion internal parity, this should always be odd. And that is why then I told you that this should be -1 to the power L plus 1. And then we were discussing about the C parity. If you recall, we had told you that we have, for example, if for example just we have a pi 0 or we have a J by psi, which is made up of CC bar quark, and pi 0 is made up of say UU bar or DD bar, then when you apply C parity, then this is U, this is U bar. Charge conjugation will make this U bar and this U, and that is equivalent to a reflection. And reflection we take by assigning a factor of -1 to the power L. Then we talked about the symmetry of the particles by considering the spins. We said that these are spin half particles, and therefore S is equal to 1 state will have 3 possible projections, and S is equal to 0 state will have only 1 possible projection. And then we said that this, to overall symmetry, we must have a factor of -1 to the power S plus 1, because S, when it is 1, it is giving us symmetric state, and 1 plus 1 will give us an even number, and therefore we had -1 to the power L times -1 to the power S plus 1. And then I told you that the Dirac theory requires for the fermions and antifermions a further factor of -1. Therefore, this is -1 to the power L from here, minus 1 to the power s plus 1 and minus 1 from Dirac theory, and therefore overall the factor is minus 1 to the power L plus s. This we have discussed in detail when we talked about charge conjugation operation. And then I told you that if n is the principal quantum number and an atomic state or these quark states we represent by twice s plus 1 Lj, where J is the total angular momentum, P is the parity, C is the charge conjugation operation. Either we are talking about a CC bar quark states or BB bar quark states. What has been observed? We have observed in the experiments different mesons, and as you can see, these mesons have different property. There is not only these resonances have been seen at the different value of the center of mass energy, but also their spin, their parity, their C parity are different. As you can see, we represented this particle as 0 minus plus, we represented this particle as 1 minus 1, where first sign is for the parity and the second sign is for the C parity. Therefore, in the experiments we have seen that we have seen many resonances, and these meson resonances, since nobody has seen an isolated quark, that means you are pumping energy to the system, you are pumping energy to the system, you are observing several resonances. This has happened with the baryons, this has happened with the mesons, and but this doesn't happen with a positronium system, because we discussed that when you have an electron positron bound system, after an ionization energy of some value, this electron and positron system, they move in the two different direction. And if you recall correctly, for the hydrogen atom, the ionization energy is minus 13.6 by n square, while for the electron positron system, this is minus 13.6 by 2n square. Therefore, depending upon what value of n is, you supply that energy, you have a separate electron positron system. And therefore, initially it was thought that the electron positron system, the potential, that is a Coulomb potential, that would also work for quark anti-quark system. But suddenly, very soon it was realized that no, here we have a minimum energy. After that, this electron and positron, they fly in the different direction. Here also, on the other hand, we find out that if we are pumping energy to the system, these particles give rise to different resonances, and you can never separate them. Therefore, we cannot have a bottom quark flying away, or an anti-bottom quark flying away, or charm quark flying away, or anti-charm quark flying away. They always exist in bound state. You cannot have an isolated quark or anti-quark. Now, the last word on these quarks are the discovery of the top quark, which happened much later in 1995 at Fermi-Lab Tevatron, because this is a particle which has got a very high mass of around 175 GeV, and therefore we needed much larger energy to see the existence of top quark, and it was observed by the CDF and D0 collaborations. The standard model determines the top quark's mean lifetime to be roughly around 10 power minus 25 seconds, which is about a 20th of the time scale for strong interaction, which is typically 10 power minus 23, 10 power minus 24 seconds, and therefore it does not form hadrons, giving physicists a unique opportunity to study a bare top quark. The top quark generally decays to a W plus and a bottom quark. The ratio of the decay rate of a top quark into a bottom quark to the total decay of top quark is defined by this. See, this is in the numerator we have the decay rate for the top quark decaying into a W plus and a bottom quark, while the bottom we have different flavors of quark, B quark, S quark and D quark. We are summing over all the possible decay rates of top quark into W plus B, top quark into W plus S, and the top quark W plus into D. And what has been experimentally observed, that this value is around 0.957. That means predominantly a top quark decays to W plus and B quark. Now, with the discovery of top quark, we had the again obeyed the Glashow symmetry. We had 6 leptons, 3 generation of leptons. In each generation, we have 2 particles, one the charged lepton and another is the neutral lepton. Here we have 3 generation of quarks, and these quarks are U, D, C, S and TB, up, down quark, charm, strange quark, top and bottom quark. While in the weak sector, we have up D prime, C, S prime and T, B prime. Like we had the mixing in the, when we considered 2 generation of quarks, when we extend these 2 generations to 3 generations of quarks, then this mixing angle, remember we wrote D prime S prime as cos theta C sin theta C minus sin theta C cosine theta C ds. Now let us write it as VUD, this as VUS, this is similarly for the other case. Therefore, the important point is that when we are writing VCD, VCS, the important point is that when we have 3 generation of quarks, we will have VUD, VUS, VUB, VCD, VCS, VCB, VTD, VTS, VTB. That means again a unitary matrix, that is a 3 cross 3 matrix. But the important point is that this bottom quark and top quark, they are much heavier than up, down, strange and charm quarks. Therefore, mixing of these very heavy flavors of quarks, they don't take place much with the masses of to those quarks which have got very less masses. And therefore, the mixing angle that we talk about here, that dominates, these are almost negligible. Similarly, that is true for this mixing of U quark with the bottom quark, C quark with the bottom quark, or top quark with the D quark, or the TS mixing. This is almost negligible, and that is why you remember this is equivalent to cos 13.1, this is equivalent to sin 13.1, this is again sin 13.1 and cos 13.1. And as you can see, when we are talking about heavier quarks, the mixing, these values are almost 0, while this dominates. Either you go from top to bottom or you go from left to right. And what you find out that this square, mod of a square, which should be close to unity, is indeed found out to be these values. Either you take the square of these and add them up, or you take these and add them up. And this is what is known in the literature as Cabibbo-Kobayashi-Masukawa matrix. Remember, Cabibbo gave a 2 cross 2 mixing matrix, while when all the 3 generations of quarks came, instead of 2 flavors, we had 3 cross 3 mixing matrix, which is the extension of Cabibbo matrix. And this was done by Kobayashi and Masukawa, and that is why this is known as CKM matrix. Now let us stop here, and in the next class, we are going to talk about the selection rules in weak interaction processes. Thank you very much.